Hi everyone, this video is on how to use the Euclidean algorithm to solve linear Diophantine equations. Long title, but hopefully it'll make sense. So if you're watching this, hopefully you've watched the video on Diophantine equations or you know how to do those. And hopefully you've watched the video and know how to do or know how to do the Euclidean algorithm, because we're going to combine those two obviously in this video. So to start with, this is the example that's in the summary. I'm going to go through this and use this example to explain what I'm doing. And then I'll show you a different question and do that one as well. That's a little bit more complex. So firstly, we're going to apply the Euclidean algorithm to this. And what we're doing by doing that is finding the highest common factor of the two values that are here, which is the first step of solving Diophantine equations. So you might not need the Euclidean algorithm to do that, but it is handy to use it because you need it for the next step. So even if you can see that the highest common factor of 22 and 6 is 2, still use the Euclidean algorithm, because then you're going to use those equations to solve for the Diophantine equation. Hopefully it'll make sense. So what we're going to do is, firstly, we're going to apply the Euclidean algorithm. So we're going to say 22, we're going to use it to find the highest common factor of 22 and 6. So we take the highest one and write it in terms of the smaller one. Then we say, okay, if that's the case, then 6 in terms of 4 is 1 and 2 remainder. So then 4 in terms of 2 is 2 lots of 2 with remainder 0. And because we've gotten a 0, that one is our answer. So the highest common factor between 22 and 6 is 2. Now that, hopefully you should know that already. You should have been able to do that pretty easily, but still use the Euclidean algorithm, because we're going to undo or use them backwards now to solve for our Diophantine equation. Because remember, our Diophantine equation was this. Now this question's a little bit handy because the highest common factor just so happens to be what the Diophantine equation is equal to. So what our plan is now is to go backwards here and get the number 2 in terms of 22 and 6. I'll show you what I mean. So based on this, I can see that 2, which is there, is equal to 6 minus 1 lot of 4. So 6 minus 1 lot of 4, which we know is just 6 take 4. Now, the reason I'm doing this is because it's undoing this equation. And now 4 can be written as 22 take away 3 times 6. So 2 equals 6 minus. Now 4 we're replacing with 22 minus 3 times 6. And the reason we've done that is now we have the number 22 in the equation and the number 6 in the equation. And that's what we want, because we want to solve for that Diophantine equation. So let's get it in terms of that. So we know that 2 is equal to 22 times negative 1, because that's negative 22. And then we've got 1 lot of 6 plus 3 lots of 6. That's 4 lots of 6. So what we've just done is we've written the original Diophantine equation, but now instead of values of a and b, we have negative 1 and 4. So what that means is we have found the first solution of the Diophantine equation. If you remember, in the steps to solve for a Diophantine equation, the very first step is find a simple solution. And generally we use intercepts or something like that. But you can see with this equation, it's not easy. There's no obvious value of a and b that give us a value of 2. But now we have one. We know a is negative 1 and b is 4. So then we can use that and put it in the general solutions for a Diophantine equation, which I've given in the summary here, to solve for that Diophantine equation. Let's do another one, and I'll go a little bit further with this one. So this is not the one in the summary. So the one in the summary, hopefully you can obviously read through that and figure out what you're doing based on what I just did. But this is a different one. So the first step, we want to find the highest common factor of 3 and 5. Now, again, you should be able to look at that and say the highest common factor is 1. We know that. They're both prime. However, we're going to use the Euclidean algorithm. So take the highest one and write it in terms of the smaller one. So that's 1 times 3 plus 2. Then we take the 3 and we write it in terms of the 2. So 1 times 2 plus 1. Then we take the 2 and we write it in terms of the 1. That's 2 times 1 with no remainder. So because we've got a 0 remainder, we're done. And 1 is the answer to the highest common factor of 3 and 5. Now again, we didn't need to use the algorithm, but we did because we want to now undo it. So now we know, looking back to here, we know we can write 1 as 3 take away 1 times 2, which is just 3 take 2. And then 2 we can write as 5 take away 1 times 3. So 1 will equal 3 minus, now instead of 2 we're going to write 5 take away 3, or 1 lot of 3. Now the reason we've done that is because now we have 1 in terms of 3 and 5. So we can write that as 1 equals, now the equation is 3x minus 5y. So 3, and there's 3 plus 3, so that's 2 lots of 3, minus, and it's take away 5y, take away 1 lot of 5. So if we expand this top one, we'd have 1 equals 2 lots of 3 minus 1 lot of 5. So all I'm doing is writing that in terms of what the original Diophantine equation looked like. So 3x take 5y. What you'll notice though is that we have 1 equals that, not 38. So what we can actually do is just multiply everything by 38. So we'd have 38 equals 3, or 38 times 3 times 2, minus 38 times 5 times 1. And if we do that, we can just multiply that 38 in the bracket. So it'll be 3 times 76 minus 5 times 38. Now that looks like exactly what we have here. 3x take 5y equals 38. 3x take 5y equals 38. In other words, we've found out that our x0 is 76 and our y0 is 38. That's our first solution. Now, that would have been pretty difficult to figure out without this process. So that's why this process is vitally important. Because now we can use those general solutions to solve for this. I'm just going to go back and go to this section where those solutions are given. So now we know x is x0, which is 76, plus b, which is our coefficient of y, which was, I'm just going to rewrite the general equation. So 3x take 5y equals 38. So b is negative 5. And then the common factor was 1. And then y is our y0, 38, minus a, which was our original coefficient of x, so 3 over the common factor of 1, t. So now I know that the general solutions to this Diophantine equation is that x has to be 76 take 5t, and y has to be 38 take 3t. So now if I sub in t equals 1, t equals 2, t equals 3, t equals negative 1, t equals negative 2, etc., that's going to give me solutions to this Diophantine equation. And that's how you use the Euclidean algorithm to solve for the Diophantine equations. I hope that makes sense. It is a little bit tricky, especially when you first do it, but use the video, get help, and consolidate, and obviously ask questions.